Thanks, Vicky, for that introduction. And I also like to thank the organizers for inviting me to give a talk on our latest achievement. It's in superhuman racing in this Gran Turismo video game, where we outraced four of the world's best GT Gran Turismo drivers in a Grand Challenge event last year. We call our AI GT Sophie, or GT stands for Gran Turismo. After that introduction, I think mostly I can skip the slide, but let me say a few things here that probably I've missed out there. My PhD was in continual curiosity-driven reinforcement learning. That's where my research interest stems from, which is on reinforcement learning theory and applications. But for those of you who might bump into me later on and not interested in reinforcement learning, let me broaden the topics there. I like to travel. I hike a bit. So I have collected several experiences that I can share. And I can talk whole day on cooking. I have been with Sony AI since its inception in April 2020. The team is spread around the world, mostly remote workforce in North America, but we have physical offices in Tokyo and Zurich. Currently, there are four flagship projects, ongoing flagship projects, one on gastronomy, AI ethics, and imaging and sensing, and gaming, which is where I'm part of. If you're interested to know more on any of these flagship projects, you can visit our website, ai.sony. Our success with GT Sophie was recently featured in the Nature article of February issue. This success was a combination of great computer architecture, lots of data, top-notch engineering, and a few algorithmic and methodological insights that I believe may generally be applicable beyond the domain of Gran Turismo. Those who have not had an experience playing Gran Turismo, I think you should just stop, or maybe wait until my talk is done and then go get a hold of PS4 or PS5, and then experience the game. It's not just a video game. It's a complex, realistic driving simulator, which models realistic physics like slipstream effects, tire slip, impacts of downforce and traction, and a lot more. It's actually a precision act, so it's often used by professional drivers to practice, and it is used in the FIA's Virtual Olympics. And for the Grand Challenge, we had two events. One was in July and October last year. The July was where we tested out our AI, initial prototype of AI, and October we had the main event. In both these events, we raced against the four best GT drivers. Again, for those of you not aware of the scale at which Gran Turismo competitions are held, it's worldwide. It's at the similar scale of Formula One, maybe. There's a huge fan following. There's Nations Cup. And these four drivers are crazy good in terms of driving these cars. And so we raced our AI against them in a three-track, three-car combinations. We picked the famous Seaside, Lago Maggiore, and Saat racetracks. And then the cars that we picked are also one of the top, Mercedes, Porsche, and the blinding speed Red Bull car. I'll be covering some of this later on my slides. Okay, so here's a sneak preview of what to follow of this talk.
There's very few places where you can go out and say, I'm going to build an AI and I'm going to make it truly superhuman.
We're going to create artificial intelligence that will unleash the power of the human creativity and imagination.
Gran Turismo Sophie is a super exciting project. It's an amazing AI research and development activity.
There are many racing games where the physics is half done, but in Gran Turismo, that racing sensation that the players get, that's really at the core of the game.
この車文化、車という存在をもう丸ごとビデオゲームの中に再現したいなと思ったんですね。
Because of the realism of the game, it is actually very difficult to program agents.
We spent a lot of time trying to figure out what things we needed to change in order to get that superhuman performance.
Why are we building this GT Sophie agent?
This is not just a technical breakthrough project. It really is about bringing AI into the hands of the game developers who are going to build the new experiences for the players.
本当にすごいアグレッシブで、これからもっと一緒にレースをしていきたいなっていうふうに思いましたね。
Okay, I hope that got all of you pumped up. And now let's see how we actually trained the GT Sophie agent. Instead of employing the approach of hand engineering control policies, which can be really tough, especially in domains like GT, we used this technique called reinforcement learning, where we learn the control policy by scratch. And here's a general, high-level overview of a reinforcement learning paradigm. At the core is the AI agent that is constantly updating a policy. A policy is basically a mapping of the current observation that the agent sees to an action that the agent can take. And this, when the agent takes the action, the environment state changes, and now the agent gets a new observation. In addition to the observation, it also gets a reward, which is basically a scalar value indicating how good the previous action that the agent took. The goal of this learning pipeline is to maximize the accumulation of future rewards, and then this process actually makes the agent learn a policy that would make it perform best in racing. To train GT Sophie, we partnered with Sony Interactive Entertainment to build a modern reinforcement learning training platform with access to thousands of cloud-based PS4s. At the center of the architecture is a trainer, which is basically crunching all the data to update the policy. The policy is then passed on to a set of asynchronous rollout workers, where each rollout worker is connected to a PS4. The rollout worker's job is to send an action to the game and then make that observation, and also compute the reward, and then pass that information back to the trainer. So for the time trial mode of the game, that is where there are no opponents, and the goal is to just get around the track. We used like about 10 PS4s, and we trained the agent for around 7 to 8 days. And for the versus mode, where there are opponents around, we used 21 PS4s and trained roughly 8 to 12 days. The trainer has a single GPU and uses about 55 gigs of RAM. So here's an overview of all the challenges that we had to solve for GD Sophie. So one of the first things that we had to do was get GD Sophie learn how to go around the track as fast as possible. So it has to understand the car dynamics and also take those precision actions and maneuvers so that it can get the fastest lap time. And then the next thing is, in the presence of opponents, we had to make a GD Sophie understand how to not just go fast, but also navigate around, and then make those decisions like when to overtake or when to block. And finally, we also had to make the agent understand some of the fine but imprecise racing norms or racing etiquette. For example, like you're not supposed to collide the other cars, and you're not supposed to go switch driving lines at your own will. So I'll be covering some details of these challenges more in the upcoming slides. Let's now focus on training the time trial mode. In the time trial mode of the game, so there are no opponents. And the first thing that you do when you're training a reinforcement learning agent is figure out what are the features, actions, and rewards. So the features that we used are state features that include 3D acceleration, velocity, and inclination, most recent actions, tire load and tire slip angle, position and orientation along the course, and a 3D representation of upcoming track points. This is to give a feel for what's going to come. And the agent takes actions at 10 Hertz frequency along 2 dimensions. The first one controls the throttle and brake, the second one, the steering angle. The agent was rewarded for making progress along the course, so more progress meant more reward, and also was penalized for going off course, wall hits, and tire slip. We used the state-of-the-art reinforcement learning algorithm called the soft actor critic, and we came up with a variant of it that best fits to the task. It's called the quantile regression with multi-step. I won't be going into the details in the interest of time, but one of the things I want to mention is the design of these features and rewards went through a huge process of ablation studies and tuning analysis. Here are the results of the time trial mode. The first plot here shows the distribution of the best human lap times on the track Maggiore. The blue bars here represents that distribution, whereas the orange lines actually show the GD Sophie's progression during the course of training. After 4 hours of training, it actually gets close to 150 seconds of lap time. 8 hours of training, it gets pretty close to the built-in AI. And after 24 hours of training, it's in the top 5 of the best humans lap time. The bottom plot shows the final policy of GD Sophie, and then how it actually compares against the best times ever recorded for Maggiore. And you can see that the orange bars here representing the GD Sophie's final policy variance is around the best time of human time. And you can see that GD Sophie does break that barrier of superhuman several times. Now, and this result is even better for the racetrack SART, which is much longer, and you can see that the policy variance is even beyond the best time that was recorded by human. So, where is the AI better? If you look at the bottom plot here, it actually shows the gap of human to Sophie and plotted against race time. And you can see that there are these dips correspond to those colored regions, and these colored regions are actually all those curves in the SART racetrack. So what AI is able to do better is take those turns, take those corners at a much faster pace and precisely and in a precise manner. And this is where humans actually lose the battle. Okay, so with that being the time trial mode, now the challenge, it becomes even more challenging when you throw in opponents with the AI. So now the challenge is to not just be fast, but you also have to navigate around the opponents. And for this, we had to make our GD Sophie aware of the opponents around it. So we gave it a representation of the opponents that included relative position, velocity, and accelerations of cars in front and behind. We also made the agent, we also gave a reward term for overtaking or pulling away from each car within a radius. So this is an added incentive to our AI agent. In addition to the representation, we also gave it more penalty terms for not breaking some of the norms of racing, like no collisions. Some of the videos you can find later on our website, where early days of training, the car actually collides with other opponents and then throws them out of the track. So yeah, we had to tune that behavior by giving additional penalties for all sorts of collisions and also side swipes. So one important thing about giving these penalties is how do you actually weigh, how much weight do you actually put on these rewards? So we learned it the hard way, in the sense in the July event, what we noticed was that we actually set these weights too high, which made our agent very timid. And this is a snapshot of the July event. You can see that the human racer is on the right and is trying to get closer, checking the nerves of GD Sophie. And GD Sophie turned out to be, at least the initial prototype of GD Sophie turned out to be timid, and it starts to apply brake, which is indicated by that yellow circle there. Luckily we noticed this and then fixed it for the final event in October. In addition to the rewards and representation, one of the things that we also made our agent aware is different racing situations that it could come across when it's in the presence of human opponents, especially the best human opponents. So for that, we actually made the agent, our GD Sophie agent, to train in different configurations, with 1v0 being the time trial mode, 1v1 where there's only one opponent, and so on. And also we trained it in different configurations like grid start, slipstream, where it can actually learn to take advantage of the physics of slipstream to make a pass. And also special situations, track-specific situations like final chicane, which is actually very crucial to do very good. It's often called the chicane of death for the racetrack start. And finally, to balance training and all these subtasks, we use stratified sampling, so that it actually doesn't forget or it actually learns uniformly across all these tasks. In order to prevent the agent to not be timid, at the same time not be too aggressive, we also design the opponent populations during its training to promote sportsmanship. Unlike simpler domains with reinforcement learning training, the policy did not converge to neatly to a point where you can just pick it up and then use it. But instead here, because of the changing distributions of this complex domain, GD Sophie's policy waxed and waned some of the skills. So we instituted a mix of automation and manual checks to find the best policy. So the process involves pulling out checkpoints of different runs and then evaluating those checkpoints across a range of metrics and then picking the best performing checkpoints as a snapshot of policy models, and then do an actual policy versus player evaluation, rank those policies based on who came first, and then finally do a human test. We have one or two good players of GT in our team, and then finally pick the one that felt mostly sportsmanship, with all the skills intact. And then finally, that turns out to be the GT Sophie that we used for our event. So here are the race results. So let me first show some of the tactics that GT Sophie picked up in the seaside track. The first video on the left shows the driving lines of GT Sophie in the time trial mode where there are no opponents. Take a note of the driving line that it takes. So it went into the turn. Basically we call it inside out. So it goes in, takes the apex, and then comes out. And this turns out to be the best way to hit a turn. And now you can see the same policy with an opponent around it. Now it's unable to take that inside out driving line. Now it ends up taking the next best line, which is like sticking around the outside driving line. By the way, these are the videos that were collected from the event, October event. And here's another instance where now, when it sees the opponent there, tries, and then suddenly notices that there is a chance that it could take the best inside out line, then takes that inside out, and then does a pass in the process. So the point here is GT Sophie is making these split-second decisions based on the opponent configuration or the opponents around it. Here's a double pass, at Maggiore. So you can see that the humans, the one that's on the right is Miyazano. He actually did a pass, then it slows down, takes that inside out lane, and then does a double pass. The figure on the right shows the driving lines taken by two of our GT Sophie against three humans, three GT Sophies versus humans. You can see that all these lines, each of these lines are different. So it's not just following a single line, but it's actually behaving based on the current state, based on the configuration that it sees. I briefly mentioned in a few slides back how our initial prototype of GT Sophie was timid in the July event. Here's a video where, after rebalancing the weights, the agent is not timid anymore. So that's a human driver in the front, and the red car is GT Sophie. There's a nice slingshot pass, takes extreme physics into account. And the human driver tests GT Sophie, but it doesn't budge, so it just goes on. By the way, so the car on the right and the first figure there is the same human driver, so he knew about this weakness in the July event, so he tried to exploit that, but that didn't happen for the October event. So here are the final results for the July 2nd event. We started out okay-ish in the seaside track. We got the first position, but oh, by the way, so the race had eight players. So 4 players were GD Sophie and 4 were human. So for Seaside, we actually took 1, 6, 7, 8 position, and the humans took the remaining. But the resultant score was 16 to Sophie and 23 to humans. And on Majority, we did better. We got 24. Humans got 15. And but we lost in SOT because of some of the things that I mentioned about timidness, and also a few other things that we corrected later for the October event. And finally, for the October event, you can see we actually did, there was no way humans could actually catch up. So Seaside, we got 27, humans got 12, Majority 27, humans got 12, and SOT was 50, and humans got 28. So finally, we defeated humans 104 to 52. So the figures on the right shows the time to the best agent during the race, and you can see that Sophie's Sophie's race time is pretty flat, whereas you can see there's a slight dip with human race times, and this was interesting. And after talking to the players, one of the things that we found out was it's basically because of tiredness during the game, and it's something that GD Sophie doesn't actually have to worry about. Okay, so here are some of the upcoming challenges for our team and for GD Sophie. And so one of the things that we are trying to do right now is to make GD Sophie available for everyone to play in the game. So a few things that go along those, few challenges for us to do that, to make that happen is figure out computational performance. Now every game needs to have a GD Sophie built in, so we need to make sure it actually runs on PS4 or PS5. And also, we want to make GD Sophie not just be available for the best drivers in the world, but also for any driver, even like me, so we can actually have a good AI experience as an opponent. So there are a few ongoing efforts to improve the slightly larger strategic decision making. So, for example, how do you deal with tire wear, longer pit strategies, especially when you have longer laps or multi-lap races, and also deal with weather. Like I mentioned, Gran Turismo models weather really well. So there's an effect of rain on the track. So yeah, so some of these challenges would be interesting to deal for GD Sophie too. And finally, make the policy explainable and interpretable so that it's actually useful for people learning to play the game. And we are also looking into figuring out identifying the degree at which we can actually transfer these insights to other games. Okay, thanks. And you can find most of the videos, and in fact, all the race videos, the July event and also the October event on the website with a professional commentary. It's very nerve-biting, so I encourage you to check it out on our website. Thanks. Any questions?
Thanks a lot. So the question that I have is about basically the framework that they use, the duration of the project. Did you use, for example, any cloning, behavioral cloning or something from the users in the YouTube, not YouTube, but any resources that you had, this kind of thing. So more about the whole training infrastructure that you had.
So let me go back to that slide, maybe. No, so one short answer is we didn't use behavior cloning for the purpose that We didn't have access to the actual, the top racers' data. We only had access to, our teammates' data, which we didn't even fare anywhere close to the best times. For example, I was like close to 130s on this track, which is not even at the best level. So yeah, so the only thing that we did, we used was reinforcement learning, where we made the agent figure out to learn this policy by itself as it interacts with the environment. So the main hurdle was designing the rewards, so reward engineering, figuring out how to, what are the good rewards to give, positive rewards to give, negative rewards, and also the weights for those rewards. So the agent knows what, able to evaluate whether it's doing good or bad on the track. Oh, the duration of the project. Okay, let's see. So we got, we got acquired. So before Sony AI, we were Cogitai, and we got acquired around 2020. So that's when we started working on this project. And then 2021 was the event. So 6 months, 6 to 8 months. A team of 10 people. I was part of the team.
So I had a quick question on the reweighting the rewards, the kind of the sub-rewards. It's over here.
Sorry, who am I looking at? There, right.
Over here. So you reweighted some of those sub-rewards to prune that timid behavior. How do you actually go about doing that and settling on the right weights?
So one of the things that we did not do for the July event was have these additional metrics. Let's see, if I can quickly go to that slide. Right, so this process called anathlon, one of the things that we did was, after collecting the checkpoints, we evaluate those checkpoints across several metrics. One of the metrics was to check timidness. We actually put an opponent car right about next and then made it drive so that it actually mimics the, a human driver who's overconfident, whatever. And that helped.
Thanks very much. So first I wanted to say I really appreciate the presentation.
Thank you.
Sophie, I'm a huge fan of Gran Turismo generally. I had a question for you about the rewards specifically, right? There's a lot of what you mentioned seems to be almost a greedy approach to reward definition. So let's make the best decision for now. In racing, that doesn't always mean the best result for the entire race. So if you take a step back and think about the rewards for more complicated strategy, tire management, et cetera, longevity, how much more complex is it to go, take a step back, re-engineer those rewards and start thinking about more complex things? Because there is potential for a cross-applicability of something like this to real-world racing, like you alluded to with Formula One, for example. You could have something like Sophie be your strategy engineer, your what have you, and replace humans.
So one of the things about reinforcement learning is you bootstrap the rewards over the course of actions that the agent can take. And even though we used rewards that seem like that reward the agent, that seem like you don't need that kind of bootstrapping where it needs to plan ahead or for future actions. So, but that's not the case here. Maybe in that video where it does a pass, so it actually, if it was playing too greedy, then it would not know that there's a car coming from behind, and then maybe it needs to slow down and then take that pass after waiting for a bit. So even though, we gave it a dense reward, we gave the agent dense rewards just to make it slightly easier for it to figure out this complicated environment. but it still needed to bootstrap those rewards back so that it knows exactly, it knows what it needs to do in order to make those big strategic. But having said that, there is, at least we didn't have to worry about, pit strategies, which require long-term planning, long-term strategy learning. And for that, we probably need to employ slightly different tactics.
Okay, last question.
Thank you very much for the talk. My question is more on the theoretical level. In the beginning, you alluded to reinforcement learning kind of replacing control in the beginning. Do you see this success of this project being applied to other areas of the business where it uses control theory?
So, sorry, I didn't mean that it replaces control. It's just that it replaces the hand engineering of control policies. So, which is often done in, at least have been traditionally done in games, where there's a person sitting and then coding out driving lines around the track and then using heuristics. That can easily be replaced by machine learning and reinforcement learning, for example. And that is domain independent, and you can actually translate this to other domains too. Not just gaming, but non-gaming domains too.
Thank you.